So, what does it mean to be a wave, and what are waves' defining characteristics? I think that waves are not localized. They have properties of frequency, amplitude, wavelength, and speed. And they're also defined by the equation lambda equals velocity over frequency. Waves also have interference, both constructive and destructive. That is when the crests of two waves overlap. They magnify each other, but the peak and like the bottom of two waves will destructively interfere by detracting from each other. Um, One experiment that deals with light, or yeah, displaying wave-like properties, is a double slit experiment with Thomas Young. Imagining a wall with two different slits, if you throw tennis balls at the wall, you'd expect to see two piles of tennis balls behind the wall. But if you imagine shining a laser at the wall, the wave will be split into two waves, one coming from each slit, and these two waves will interfere with each other both constructively and destructively. By marking where the light hits the wall, you'll see a bunch of like piles or stripes of light um, on the wall, and this is called a diffraction pattern. So pretty much when you shoot light through a wall with two really small slits, it divides itself and will interfere to create a pattern of a, a lot of stripes. Um, by marking the point, instead, if you shoot electrons at the wall, um, if you mark the point at which the electron hits behind the wall, you'll see the same pattern. And this like begs the question: how can an electron pass through both slits at the same time and then rejoin at the end at one point on the wall? And the issue with answering this question is if you put a detector to see which slit they go through, this actually destroys the diffraction pattern. It's lost because by detecting the electron, you have to hit it with something, and that will completely change the course of the electron. This is known as the observer effect. Um, the Davidson German the Davison-Germer experiment also shows light displaying wave-like properties. An electron beam is provided by heating up tungsten, and this beam is directed at a nickel surface. The electrons are then deflected towards the detector, and when Davison and Germer did this experiment, they expected a random pattern of electrons um, bouncing off the surface towards the detector, but instead they saw a diffraction pattern similar to the same diffraction pattern shown in the double slit experiment that Thomas Young did. So again, light and electrons are being shown to be waves as instead of particles. What does it mean to be a particle, and what are particles' defining characteristics? Particles have mass, momentum, kinetic energy. They're localized and they can have collisions. Two experiments in which light or other objects display particle-like properties. One of them is the photoelectric effect. When you shine light on metal or anything really, but specifically like the effects are more seen in metal, electrons are emitted from the metal. Classical physics predicted that if light were a wave, the intensity of the light would be proportional to the rate of the ejection of electrons. It would be proportional to the kinetic energy of the ejected photons, and the frequency of the light would be irrelevant, and the time for ejection would be long. But experimentally, scientists determined that the intensity of light is proportional to the rate of ejection, and it actually has no relation to the kinetic energy of the ejected electrons. Instead, the kinetic energy depends on the frequency, and the collision time is really short. So this makes electrons seem a lot more like particles. They collide with a metal and they knock off another electron. The photons knock off another electron. And this is a collision, which is a property of particles and not waves. Another experiment is the Compton scattering. This happens when a photon is shot at an electron, which is sitting at rest. The electron will be hit off at one angle called theta, and the photon is also deflected but continues at a different angle phi. And looking at the diagram for Compton scattering, it looks exactly like an elastic collision, and it shows that photons are have at least particle-like characteristics because they're making a collision just like two tennis balls would. Um, so the two different sides to these small particles is known as the wave particle duality. And my thoughts on something being both a wave and a particle, um, I think that's very hard to wrap my mind around because it's not how our brains are wired to think. We usually see things as either a wave or a particle. We see a lot more particles in our life, in our daily lives, although we do see waves. And to think that something can be both a wave and a particle, just it's very hard to make sense of. Uh, you gave an example in class about how sound waves could have interference if you were yelling into a slotted wall, and this just was very confusing to me because I think we usually, I think it's very hard to picture that interference would allow a certain part of the audience to hear, but not another part of the audience, even if they were sitting right next to each other. But I think it's even weirder if sound showed more particle-like properties here, in which if I yelled at someone in front of me, the person behind that person would not be able to hear me. I think the bigger implications of wave particle duality is that everything that is made up of these small particles like electrons and protons, um, everything is both a particle and a wave, just as Louis de Broglie said. And it's just really weird to think that we're both a wave and a particle. Fortunately, at least I don't think that we can see the effects of this because we're too big. We can't show interference patterns through going through slits in a wall because um, those slots would have to be really, really, really small. Um, but yeah, I just think that it's something that we have to try to learn to accept so that we can continue learning about quantum mechanics. Thanks.